Hello student, today we are going to learn about the relation between Kp and Kc. So let us start. First we will write a hypothetical reaction like this is the reaction. A plus B moles of B react together and form two products, C moles of C and B moles of B. Suppose this reaction is in equilibrium, so we can write the equilibrium constant regarding to the concentration of all reactants and products. And the equilibrium constant Kc will be like this. Concentration of C raised to C, concentration of B raised to B, concentration of A raised to A, and concentration of B raised to B. So this is our equilibrium constant with respect to the concentration, which is Kc. Now we are going to derive the relation between Kc and Kp. So we are going to write the equation with respect to the pressure, that means Kp. So formula of Kp for this reaction will be like this. Here we are going to use the symbol which represents the pressure, which is P. Here for concentration we have used an angular bracket, but for pressure we are going to use a large P. So pressure of product C raised to C multiplied by pressure of product B raised to coefficient of B, pressure of reactant A raised to the moles of A, and pressure of reactant B raised to moles of B. So this would be the equation for Kp. Now we are going to establish the relation between Kp and Kc. So we will use ideal gas equation. Suppose according to ideal gas equation, PV is equal to nRT. So if we make subject as P, so P is equal to nRT upon V. Now we know that N means moles and V means volume. Mole per volume, which indicates the concentration. That means we can write this equation as P is equal to CRT. Here C stands for concentration, which is mole per volume. So now we can write CRT instead of P. In this equation, all the P will be replaced by CRT. So we can write this equation of Kp as Kp is equal to, instead of this P, we are going to write CRT. CRT for product C, power of C, multiplied by CRT of product B raised to coefficient of that product. Now in denominator, instead of this P, again we are going to use CRT and reactant A raised to the coefficient of that reactant, which is A, and CRT of reactant B raised to coefficient of that reactant. Now in this particular reaction, which is in equilibrium, we know that when reaction is in equilibrium, then temperature remains constant. So this T will be constant for all this reaction, and R is a universal gas constant. So R and T remains constant in this equation. Only the changes happen will be in this C, which is concentration. So we can write this equation as Kp is equal to concentration of product C raised to its coefficient C, and RT for C will be remain constant, so there is no need to write product C over here, but we have to write the coefficient of that product C multiplied by concentration of product T raised to coefficient of D multiplied by RT raised to coefficient of T upon concentration of A raised to A multiplied by RT raised to A and concentration of B raised to B multiplied by RT raised to B. Now, from this equation, we can write concentration of C raised to C multiplied by concentration of D raised to D upon concentration of A raised to A multiplied by concentration of B raised to B, and here we can write RT raised to C plus D upon RT raised to A plus B. So equation will be here, this concentration symbol can be replaced by this angular bracket also. So we can write this equation as C raised to C multiplied by B raised to B upon concentration of A. There is no need to write now C over here because C is inside the bracket. A raised to A and B raised to B, and this can be written like this: RT raised to C plus D minus A plus B. So this whole equation can be written as Kc because concentration of C raised to C and D raised to D upon A raised to A into B raised to B represents Kc. Therefore, Kp will be equal to Kc and multiplied by RT raised to here C plus D minus A plus B, which means total moles of product minus total moles of reactant. If they are in gaseous form, then we can write this as delta Ng. So this will be the relation between Kp and Kc. Kp is equal to Kc multiplied by RT raised to delta Ng. Now from this equation we can have three different conditions. Suppose delta Ng is equal to 0. That means if here the value of delta Ng becomes 0, that means RT raised to 0. That means RT will be 1. RT raised to 0 is equal to 1. It indicates that Kp will be equal to Kc. So if delta Ng is equal to 0, then we can say that Kp is equal to Kc. This is the first condition. If we imagine that delta Ng for any reaction is greater than 0, that means here the value of delta Ng is greater than 0. Suppose it is 1. That means RT raised to 1, it will have some value, and if RT is there, then Kp will be equal to Kc multiplied by RT. That means Kc is when multiplied by some value, then it will become equal to Kp. In that case, we can say that Kp is greater than Kc. So when delta Ng is greater than 0, then Kp will be greater than Kc. And now let us imagine if delta Ng less than 0. That means here the value of delta Ng is less than 0, which is negative. Suppose it is -1. So we have to write this as Kp is equal to Kc upon RT, because RT raised to -1 is equal to 1 upon RT. That means Kp is equal to Kc upon RT. It indicates that if we divide this Kc by RT, then it will be equal to Kp. In that case, Kp will be less than Kc. So, this is the ultimate equation of which indicates the relation between Kp and Kc, and it is very useful relation which is used in many numerical problems, and these are the three conditions regarding this equation. One more thing, students, if you want me to teach you any topic of chemistry in Gujarati, Hindi or English, then just write the name of that topic in comment box. Thank you.